Hi everybody, this video on solubility covers the last 2 pages of chapter 6 in your lecture notes. And so what you want to do is first, before you actually start watching the video, make absolutely sure you've turned your lecture notes to page 5, and then you will see exactly what you're seeing on the PowerPoint screen as I talk my way through these last couple of pages of content. So when you're ready, we're going to talk about solubility, and to understand solubility we have to know first what homogeneous means. And so what homogeneous means is that the mixture is evenly distributed. It's the same throughout. And we have lots of examples of things that are homogeneous in chemistry and in biology. As an example, coffee is homogeneous. Tea is a mixture of different flavorings, and sugar perhaps, and water, and it's all evenly distributed. It's the same throughout. The first sip of coffee tastes like the last sip of coffee. However, a good example of something that isn't homogeneous, we would say this would be heterogeneous, is like a chocolate chip cookie. Chocolate chip cookies, you take one bite and you get a chocolate chip, you take a different bite, you get a chunk of oatmeal, etc. So there's a great example of something that isn't homogeneous. All right, so when we understand what homogeneous means, a solution is simply the homogeneous mixture of 2 or more substances. And so coffee is, in fact, a solution. In a solution, we've got 2 main things that we typically think about. The solvent, and that's whatever is present in the largest amount. When we're thinking of liquid solutions, the solvent is typically a liquid, like water might be a good solvent, and then sugar might be a solute, or salt might be a solute. The solute is whatever you have dissolved in the solvent, and there might be more than one solute. One thing that's really important to understand then is how much solute is going to dissolve in our liquid solvent. And that's going to be determined by everything we've talked about in chapter 6 up until this point. Basically, it's going to be determined by the similarity of the solute and the solvent's intermolecular forces. So, for example, we talked about polar compounds earlier in chapter 5, and so when you have polar compounds and ionic compounds, they're going to dissolve really well in polar solvents. And the reason is because the polar solvents have slight negative and slight positive parts on the molecules of the solvent, and the polar solute is going to dissolve easily in that, because then the negative part of the polar solute can associate with the positive part of the solvent molecule, and vice versa. Along with that, nonpolar solutes are going to dissolve really well in nonpolar solvents, and that should make perfect sense as well. So something like gasoline is going to dissolve really well in motor oil. They're both hydrocarbons, and they're both really nonpolar. So we have a big rule that we use that helps us to understand that everything is based simply on the similarity of the intermolecular forces between the solute and the solvent, and we say like dissolves like. So substances that have similar intermolecular forces will dissolve in solvents that have those same kinds of intermolecular forces. So our most important solvent is water, and it's very, very polar. And so it's really good at dissolving polar solutes and also ionic solutes, like salt, for example. When we talk about water being the solvent, we have 2 really important words that we use to describe the solutes that dissolve in water or that don't dissolve in water. So we talk about hydrophilic substance, that's water-loving solutes that are either polar or ionic. And then we have things that we call hydrophobic or water-fearing solutes, things like oil and wax and that kind of stuff, but basically non-polar solutes. First thing we want to understand is how do polar compounds, not ionic compounds yet, but how do polar compounds orient themselves when they dissolve in water? And so how does the water, as the solvent, orient itself around the polar compound? What we can see over there on the right is we can see some water molecules with the 2 white hydrogens and the red oxygen. We can see those water molecules beginning to kind of accumulate around this particular solute. And so what we see is that the positive H's are pointing themselves toward the negative O's in the solute. And then the negative oxygen atoms, you can see, are pointing themselves toward positive parts of the solute, in this case, towards the hydrogen atoms. So that's how polar compounds are going to dissolve in water. Water orients itself as the solvent around the polar compound such that the positive part of water orients towards the negative part of the solute, and the negative part of water, that's oxygen, orients toward the positive part of the solute. Next thing to understand is how is it that ionic compounds dissolve in water. And so what we've got over there on the left is an example of table salt, sodium chloride, and you can see our orange sodium ions and our green chloride ions. And you can also see the beginning of some water molecules starting to attack that crystal ionic lattice. And what you see is a green chloride ion being attacked by the slightly positive hydrogens in water. The slightly positive hydrogens in water are going to orient themselves toward the negative chloride ion in the lattice, and they're going to work on it for a while, and pretty soon they're going to pop that chloride ion right out and surround it. And you can see it surrounded in the diagram in the center of the page on the right. So what happens? Well, we call these kinds of associations ion-dipole forces, and I'll describe them on the next overhead in just a minute. But what happens, as we just described, is the positive hydrogen atoms in water pull the negative ions out of the crystal lattice, in this case the chloride ions. And then what also happens is the negative oxygen atoms that are in water pull the positive ions out of the lattice. And what we get is what's in the center part of your screen there. You can see the sodium cations are all surrounded by water molecules, but the water molecules are all pointing their red O's, toward that orange positive sodium. And in the rightmost diagram there, you can see that the negative chloride ion has got water molecules pointing their slightly positive hydrogens toward it. So that's how we orient the solvent molecules around ions when ionic compounds dissolve in water. Hopefully you've had enough time to copy down what you need to copy down on this page, so we'll go on to the next one. What are the ion-dipole forces then? How do we define ion-dipole forces? And what we're going to try to do is summarize what we saw on that last page. And ion-dipole forces are just the attraction of an ion for the oppositely charged part of a polar molecule. And what we find is that the smaller the ion is and the larger the magnitude of the charge is on that ion, the stronger it's going to associate with a water molecule. And so, for example, if we think about their attraction to water, aluminum with a 3+ charge, and also very small, is going to be much more strongly attracted to water than will be calcium, which is a little bit bigger, and it has only a +2 charge. And calcium with a +2 charge is going to be more strongly attracted to water than the slightly larger and less positively charged potassium ion. Getting close to the end here, we need to understand then this word solvation. So solvation is simply the word we use to describe the process of solvent molecules surrounding any solute. And we saw good examples of solvent molecule water surrounding a polar molecule. Then we saw the process of a water molecule surrounding sodium ions and chloride ions. So we might say, for example, water is solvating the sodium ion. When we talk about the word miscible, what we're talking about specifically when we use miscible are two liquids that are soluble in each other in all proportions. And so vodka, for example, has about 40% liquid ethanol dissolved in water. Everclear, if you know what that is, has about 95% ethanol and about 5% water. So ethanol and water are fully soluble in each other in all proportions. A little teeny bit of ethanol will dissolve in a lot of water, a little bit of water will dissolve in a lot of ethanol, and we would say therefore that ethanol and water are miscible. All right, finally, one final point, and that is that we surprisingly probably for you, we can get nonpolar hydrophobic compounds to dissolve in very polar water. If we couldn't do this, then oxygen, which is completely nonpolar, O2, would never dissolve in water, and all aquatic organisms, fish and plants and bugs and things like that, they would all die because they couldn't get access to water. So water will dissolve a little bit of nonpolar hydrophobic substances like O2, oxygen. And so we're going to use O2 oxygen as our example here. But to try to figure out what happens, you can probably imagine that if you've got a water molecule with its slight positive and slight negative parts, as a water molecule approaches a nonpolar compound like O2, the water molecule is going to induce a dipole where there wasn't one before on the nonpolar molecule like O2. And so once the water molecule comes close to the electron cloud of the nonpolar molecule develops a slight negative and slight positive charge, as you're going to see in just a minute in the little diagram. And then the two can associate with each other, and a very small amount of the nonpolar hydrophobic substance can dissolve in water. So here's a picture of water approaching an O2 molecule in the top part of the diagram, and as they get close, then you can see the perfectly symmetrical nonpolar O2 begins to develop a slight negative side and a slight positive side, and then the water molecule and the now temporarily polarized O2 can associate, and the O2 dissolves. That's it for today's lecture. We just covered the final 2 pages of the Chapter 6 lecture notes, and I'm wishing all of you a great fall break.